So recap first. So we covered language model last week. And I told you that language model is about really creating a probability distribution over strings of text, which means that you want to know what the probability of certain string, really literally, something like probability of hello world. So the formal definition of language model is that being able to define this probability for every text in the language. But of course, we mentioned that this is very difficult because there are infinite number of possible text. And furthermore, what that means is then probably it doesn't really make sense or useful to give a probability on a certain text. It's very rarely useful. So a more useful way to use this probability distribution is predicting the next word and basically trying to generate the sentence using this distribution. And that's exactly the definition of actually generative model. So generative model has a very narrow definition that it has to be able to really compute the probability of all possible text, or not the, of course, always text. We're in the domain of text, but if you're in the domain of image, then this will be image. But it's basically what's the probability distribution of the output, the target output. So generative model is able to define that. And because of that, you're able to generate a new output instance, sample, for instance. But then, of course, it, as I've said, it's rarely used to really measure the probability of certain sentence, which is rarely useful, but more of how can you predict the next most likely word given the current input. And of course, if the current input, the current text it's empty text, then you're just trying to generate a random text starting from nothing. That will be a more of a pure language model. Okay, so that's where it's used. And we show you that, for instance, what we're interested in is usually what would be the next word being the probability of the next word being world. Sorry. Given that the current word is hello. And this is exactly by the bias rule. Very easy thing, right? What's the probability of hello world over the probability of hello? So you now you get the point why if we are able to really compute this, then it is trivial to compute this too, mathematically, of course. In reality, it's not always approximated with this prior probability, but there might be more efficient way to compute that. But mathematically, you are able to compute all these conditional probability given if you have the distribution of the every possible text. And how can we do this? So the more traditional methods, as we discussed, was n-gram language model. So that's actually very related to how we do this Bayes rule. So we want to compute really this one. N-gram. In the n-gram language model, you compute the probability of each unigram, bigram, trigrams, probability, etc. So you will be able to compute what the probability of hello in unigram space, and you'll be also able to compute the probability of bigram hello world, right? And then this is unigram, and this is bigram. So in this case, this will be a bigram language model. So really the point here is that, of course, your sentence might be really long, right? So you might be guessing the word. So I'll give you an example. So for instance, you have hello world and school. And in order to really predict what's the probability of getting this word school, a bigram language model only looks up to the word right before school. So then in that case, so what we want to really compute is what is hello world and school over hello world and. But we are making a assumption that this can be approximated with and the school. We're only looking up to the one word before the current target, right? So this is a bigram language model. You're making the assumption that you only look at two words at max in your denominator, and not denominator, in your numerator probability. If you look at three words, then of course it will be trigram, right? So here you're only looking at this, so that's why it's bigram. You can look up this will be trigram, and etc. So if you look at the entire four words, then it will be 4-gram language model. So that was like the most basic way to approach an language model problem especially before neural network. And this was very powerful. It's actually still powerful for many applications because it's very fast and it's very simple. You just need to count how many times and school appear together among all possible bigrams in the training data. That's how you compute the probability. But what's the problem with this approach is that if as n goes up, there will most n-grams that you see in the inference time will not have appeared in training time, right? Because there are about, if your vocab size is 30,000, there are only 30,000 possible unigrams, but there are up to 900 million, 30,000 square, right? 900 million possible bigrams. And if you just go on one more step up, trigrams, then it will be more than, how much is it? So you have 900 million and you multiply that by 30K, then it's like 2.7 trillion possible trigrams. And this is going up exponentially, right? So if your n is high, then it is very likely that you have never seen that n-gram in your training data, or you have seen it only once or twice, that it's very hard to really give you any interesting statistics. So that's why people usually don't go up too much when you're using n-gram language model, probably at most bigram or trigram. And here comes the neural language model, which is able to do better than n-gram when we want to consider long distance dependency. And in fact, it's very straightforward given what we learned until now. Basically, neural language model is SIG to SIG model without the encoder side. So you just have the decoder where the encoder can be, maybe you can consider it as an empty string. Then it becomes your language model. And model language models are mostly based on transformer, just like how other seq-to-seq or encoder models are based on transformer. So it's good to know, because if you read the recent papers, then that's something that people kind of assume. Yep, so actually, yeah, I talked about this. We had we had a discussion about syntactic parsing, right? So I told you that syntactic parsing was very important for feature extraction before deep learning took off in NLP. But now most people directly really optimize for a target task than utilizing these intermediate structures. But I don't mean that these are not important. It's just that syntactic parsing was very crucial for doing any target task that involves natural language back then in like 2013, 2012. But then after deep learning, syntactic parsing is, especially these days, is not really used for features, but more of it's more of a target task that linguists are interested in, because you want to understand how the language is structured. So that's exactly because syntactic parse is usually not the target of the task. That's a really important thing that you need to be aware of when you're doing NLP, because in many cases, when you're trying to formulate a certain task into a machine learning problem, the most straightforward way to formulate the problem is that your input to the machine learning model is exactly the input of your task, and the output of your model is the output of your task. And when you listen to this, you might be thinking like, what am I talking about? Like, it's the same thing, task and model. And my point is that it's not, because when you're trying to achieve certain task in real world, you'll be really thinking about which part of the task you're going to use the machine learning to take care of it, and which part of the task you'll be using other things. And that means your task is going from input to output from, of course, your user or your customer. But in reality, in many cases, there's something happening in the middle, and what the model is taking care of is really only part of it. There is something happening here and here, basically. And syntactic parsing was very useful in early days when these models were not good enough, that you had to have really a lot of pre-processing and feature preparation before the model gets applied. So the syntactic parsing was playing role here a lot. Use an off-the-shelf syntactic parse to enumerate these features, and then you use that with the original input into the model so that you can get some output. But as the deep learning advances, the need for such off-the-shelf syntactic parser has decreased since then, gradually. So nowadays, I think we rarely see any model, especially state-of-the-art model, uses syntactic parser. When there is enough data, of course. When the data is scarce, still syntactic parser is very useful. But I mentioned this because we're going to cover semantic parser, and it's a bit different because semantic parser, in the case of semantic parser, really the task is usually exactly equivalent to the model. So we're going to cover that soon. But let's go back to the slides, syntactic parsing slides. Yeah, we're taking a lot of time to recap, but hopefully we can be very brief about the context-free grammars. So do you recall these? So I told you that the syntactic parse of sentence is usually about defining what the role of each word is and how can you build a tree that makes, I would say, syntactically nearby words are actually nearby in the tree space. And we mentioned that the important thing I wanted to mention is that the grammar here, it's something that you translate a bigger chunk into smaller chunks. So let's go back to this thing again. So we're talking about this noun phrase and verb phrase. And noun phrase is here John, and verb phrase is met her. And this is one way that linguists make the first separation starting from a full sentence. So S is a sentence. And you can, for many sentences, sentence can be broken down into these two constituents, NP and VP. And they can be further broken down into sub-constituents. For instance, verb phrase gets broken down into VBD and another noun phrase. So this breaking down process, which is, you can think of this as a transition. There are many words to describe this, but I'll say it's a kind of transition. Then there are many possible transitions. And you can start from S and move to NP and VP, or it can be maybe you have an aux in front of NP and VP, or it might be just VP alone in some cases. And these rules, basically, these rules together define the grammar with the lexicon, of course. Lexicon is all the vocab words. It's a fancy way of saying the vocab. And I told you that there are two types of nodes. One is non-terminal, which is S and PVP. These things are non-terminal. And actual word in the sentence are the terminals. So every leaf node is terminal, and every non-leaf node is non-terminal. So it's a very straightforward definition. And we mentioned that there are a lot of different ambiguities. There isn't always single correct answer. And it really depends on the semantics of the sentence or the meaning of the sentence. So you might be still wondering what the difference between syntax and semantics. I'll be discussing that soon, but for now you can think of it as syntax is the structure, semantics is the meaning. But the ambiguity of the parse happens because of the meaning. So syntax and semantics is not completely separable. Your sentence's syntax depends on the sentence's meaning. Here we saw that the in my pajamas phrase or that constituent can be either attached to elephant or I. And of course, probably it's you or it's I who is wearing pajamas, not the elephant in many cases, right? But that's more of a semantics. We have some context. We have some information about the world or some prior about the world. But you never know, like maybe in 100 years, maybe elephant will be wearing pajamas too. So you can never really ascertain that, but we can at least try to give some probability. And then we might be able to say, oh, maybe this parse is more probable. So we might want to give this parse something like 0.99 and this 0.01. We're not ruling this left parse completely, but we're giving much less probability that this parse might be correct. So this actually motivates why we need some probability in our grammar too. And I mentioned that the transition and the lexicon constitutes grammar. And when I say grammar, in this lecture, at least on today's lecture, at least, I'm talking about context-free grammar. So this is not the only way to define the grammar. In fact, context-free grammar is probably the simplest grammar. There are much more complex grammar. And of course, human language is not the only language. Programming language is also a language, and the grammar that's being used in most programming language is much more complex than CFG. So CFG is kind of starting point, and I think many of you know what this is if you took programming language class and what I mean by. But CFG is very convenient because the grammar can be very formally defined and also very, I would say, relatively easily defined. And it consists of N, T, and S, and R. And N is the set of non-terminals, S, M, P, V, Ps. T is a set of terminals, which is basically the lexicon or the vocab. Right? And there is a star symbol, which is not too much important usually. And R is the rules, right? So how each non-terminal can be transitioned into either other non-terminals, e.g. S to NP and VP, or maybe they will be differentiating into terminals. Then in that case, we also need rules. And it makes sense, right? Because in many cases, for instance, if you have a noun, then this noun can be assigned to many possible words in lexicon, but you know that many words in the lexicon cannot be noun. So even if our vocab size is 30,000, the probability of certain word being noun can be 0, right? So that means that rule will be not rule will be very important for transitioning from the non-terminal to terminal as well. It's more of an obvious thing, but just to make sure that you understand that. Okay. So what we can do with PCFG is then, if we have the PCFG defined, so that means then we have some probability on the rule side. So the definition here was just the context-free grammar, right? But what if we add the probabilistic aspect to CFG? Then other things are all good, but we just have to add just one more thing, which is what will be the probability of each rule in the R. So that's exactly what it means. And we just need to basically define, okay, given S, what's the probability that we'll be transitioning into VP and NP? And in our previous example, we saw that there are 3 in this grammar. Of course, this doesn't mean that each of them is equally likely. So if you want to do this really formally, then you will have to assign a certain score for each, and most statistical approach will be counting how many times S turns into NP and VP in our training data compared to other things. So we'll be able to get those numbers if we have training data, right? So we'll be able to define these probabilities for every rule. Then with this rules, with this probability and the rule, what we can do is then we can at least find the most probable parse, whether it's efficient or not. I hope you agree with that. And that's exactly because, well, once we have defined this, then the probability of certain parse is just the product of the probabilities of the individual rules. So going back to the slide, I'll show you an example. So for instance, if you want to compute the probability of the right parse, this will be just exactly P of MP VP given S, and you compute what's the MP going into pronoun given MP, and you I'm multiplying everything, by the way. So, and you compute what's the probability of pronoun turning into I. So you're done with the left branch of the tree, and you go into the right branch, which is now what is the probability of VP turning into VP and PP. Okay, I'm running out of space, and you get the point, hopefully. So you just have to multiply all these individual probability of each rule to compute what's the probability of the final parse. Okay, so that's good. So that's exactly what we have in the next slide, right? So we can compute the probability of each rule, and then we just multiply all of them to compute the probability of the final parse. And we saw, remember that this was also another ambiguous case, because you have a sentence booked a dinner flight, and it's ambiguous whether the dinner and flight goes together or book, dinner, and flight are all parallel, right? So it's the whether your dinner is actually you know so actually what I meant is that, is it that you're referring to the dinner flight everything with the determiner the, or is the just referring to the dinner, not the flight? So it's basically where the is referring to, is it dinner or dinner flight? It depends on whether you'd consider dinner flight as a constituent first, or you first deal with the dinner and join that with the, and then join with flight and book. So you see where the ambiguous case can happen even as in a such simple sentence. And maybe you might be able to compute and determine which is more probable parse by if you know all the probabilities of the rules, and then just compute the final probability and compare between them. So it's just an example, and we saw that we just have to multiply everything. And in this example, the left parse was 2.2 times 10 to the power of -6. This is a probability of the left parse. And the right parse is 6.1 times 10 to the -7. And in this case, of course, then the left parse is more likely. So if your model is able to decode that, then it will say the left parse is the correct one. So again, this is a recap of what I said. How do you compute, then how to determine what's the probability of each rule? The simplest case is that you just count in your training data, and then just divide those counts. So it's just you count how many times A transition into B, or I mean alpha transition into beta, and then just count everything that alpha transition into. Then in that case, then transition probability into beta given alpha will be exactly just this. It can be computed with this simple division, and I think this is very straightforward. It's very elementary probability theory, right? So one of the most popular data set is called Pantry Bank. So it's one of the first data sets that, first, number one, it's big enough, and number two, for big enough for any machine learning techniques to be used even before the deep learning era. And number two, they were very carefully created on diverse linguistic tasks, including constituency parsing, which is one type of syntactic parsing. And if you look into the data, then you will see that data looks like this, and it's very familiar, right? So you have a S. S can be divided into two. Shall use another color? It's a tree, right? And then MP is going into the move right away. And VP goes to, where is it? Yeah, VP goes to two things. One is, I think, so this is just 1 second. Yep, so in this case, then leaf node will be the and move, and VP goes to followed and the MP, and MP goes to MP and PP, and MP goes to A and round, PP goes to off and MP is again three children nodes, and each has also more children nodes. So you get the point how the tree is structured, right? So that's how the tree bank records the tree structure. And they're very long, it's complex sentences, and a lot of clauses, nested prepositions, etc. So when people are trying to create a syntactic parser, they use this data set to train their model. And then once the model is trained, then you're able to spit out this structure for unseen sentence during inference time. Okay, so we're gonna just, so there's you can try to refine the grammar by using the syntactic parse. I'll just skip this. It's not too much, have much time, but I'm gonna see where we're gonna stop with these slides. Okay, so, but I wanted to also mention that this is a very strong assumption that we have this very strong assumption, right? So what is the probability that the PRP turns into she, or what is the probability that MP turns into PRP? And when you're trying to compute, you're looking at this part, right? What is the probability that you're gonna transition into given MP? This is very naive in the sense that it's a very naive formulation of the probability. You do not know what happened before or what happened at the top, because the correct way to define this probability is actually what's the probability of MP turning into PRP given MP and its parent is S. But we, in the original context-free grammar, original PCFG, we assume this independence. Once the MP is given, then it doesn't matter what's above MP, which is a very strong assumption that might not hold true. So what people have done after they have formulated syntactic parsing into PCFG is that, okay, we cannot just assume that this MP turning into PRP probability is independent from what the parent of MP is. So let's mark each non-terminal with what its parent is. That's exactly this this mark, the, what do you call this hat mark, this thing. And in this case, then you're considering NP hat as a non-terminal instead of NP. So you'll be able to differentiate between NP hat S and NP hat VP, which were not differentiable without considering what's above that constituent. So that's very useful, right? Because now you're able to make the probability rule separately for these two cases. So you can think of this as a more of a latent variable, right? Because you have a latent variable, what's above it, and we have been ignoring it, but we actually don't want to ignore it. We want to actually consider that so that we are able to differentiate between these two noun phrases and build the probabilistic model separately for these two different noun phrases. So that's exactly what's called, um, where is it? Let me see. Yeah, so that's what's called, um, I'm actually having a bit of a problem remembering which one was which, but so basically, let's see. So this is the, yeah, manual text splitting. So I think they used the term lexicalization to refer to this, if I'm remembering correct. And the difference between lexicalization and manual text splitting is that instead of giving this hat to indicate what's above, they actually try to explicitly differentiate between different kinds of noun phrases. And that will be, of course, determined by the humans. So that's why it's called manual. And what I mean by is that linguists make make a list of different kinds of NPs, basically. Oh my gosh. Make a list of different kinds of NP so that you can consider each NP differently. And this was done manually, but sorry. But there was another work after that, which basically allows the model to really choose which type of NP it's using instead of oh my gosh, which type of NP we're using, which is the latent text splitting, this work. And so what in this work, what they did was that instead of manually defining which class of NP each belongs to, so here the 3 and 7 are the different kinds of NPs, depending on what they do in the sentence, what their role is. In the latent text splitting, the model doesn't have any prior knowledge about these these tags. They just make the tags as they go in order to improve the final accuracy. And that was the work in 2005 and 2006 called latent text splitting. So I think we're going to have a short break at this point, and we're going to finish up the syntactic parsing with a brief description of a CKY parsing, which is about how we can obtain the parse efficiently. So I'll come back in 3 minutes. See you at 3:23. All right, all right. Welcome back. So let's finish up with the syntactic parsing and move on to semantic parsing. So you might have been wondering, given all these rules, so is finding the best parse that in this case best is actually really absolutely the best parse that gives the highest probability, whether that getting that is efficient and it's computationally efficient. And the answer is actually that if you do this brute force way, then it will be very inefficient because it will be exponentially many ways to create the parse given the rules, all different rules. So you shouldn't do that way. You shouldn't use brute force, but rather you have to use dynamic programming to build up the tree, starting from the leaf nodes. So that's exactly what CKY parsing does. So it's named after three people who created these algorithms. I don't remember exact. Oh, there you go. You see why it's CKY, right? Because it's from these three names. Second. C, K, and Y, right? Of course, these people created the algorithm in different years, but they are all recognized by the CKY name. And so you can think of it as dynamic programming that allows you to create the final parse in an efficient way. But still, it's not linear time, by the way, but it's not exponential time as well. So you can see that this works. You can find the best parse always without worrying about if this is like a non-optimal parse. It's actually very exact. That's exactly the point of dynamic programming. So I'm not going into too much details, but I hope you can take a look. You can search for CKY. Actually, I'll put some additional materials if you're interested in how you can actually compute the CKY algorithm. You can actually run the CKY algorithm to get the best parse. Yep, so I'm gonna skip all these things. So you might be wondering how you can evaluate the constituent parser. And the way that most people do is they have recall and precision computed. So recall is the number of correct constituents in hypothesis parse of S over the number in the reference parse. Precision is same in the numerator, but you count how many are in the hypothesis parse. So just typical way of computing F1 at the recall and precision, and you usually report F1, which is 2PR over P plus R. And you can see that in the early days, it was about 1999. You have this lexical methods, which was 88.6, and then more recently, there were other, I'll say it's not really recent, it's like 2006 and 5, and they were going up to like 92.1, and it's much higher these days if you use neural networks, but hopefully, yeah, you get the point how it was approached in the older days. Okay, so I think we talked about a few syntactic ambiguities. I'll be probably skipping these. I think it's pretty clear at this point what I mean by syntactic ambiguity, hopefully. So there are a lot of ambiguities. There are different types. People have some terms to use. Terms they use to refer to different types of ambiguity. For instance, prepositional phrases, particle versus preposition, etc. So I think, of course, I think we talk about this. The ambiguity mostly happens because we don't have we need the, and in order to resolve these ambiguities, we usually need the information about the world. In this case, in our previous example, for instance, how can you know that the whether it's me or the elephant who is in pajamas? And you can exactly know about that if you have the world knowledge. So that's why the world knowledge is important, and as well as the context information, because it will also depend on what the context is. If your story is really like sci-fi, which is like 100 years from now, where the elephants are like humans, then maybe it's not too weird to say the elephants are in pajamas. So not only the world knowledge, but also the context of the text that you're in right now is really important to be not resolve these ambiguities in the syntactic parsers. There are a lot of other things, but I'll probably skip these. And I want to briefly talk about dependency parsing. It's a really important topic though. So up to now, we talked about constituency parsing, which is one type of syntactic parse, but it more a bit, I think, a bit more easier to use parsing syntactic parse is dependency parsing. It's because it's less rigorously defined. In dependency parsing, what you're just doing is that you just basically define the relationship between the words instead of creating this abstract tree with a lot of different non-terminal nodes. And also, of course, it's still a tree in the sense that it has a root node and it has its children, but then there is no abstract nodes, non-terminal nodes. Every node here is terminal nodes, and the only way that you define the syntax is through which words are related and also how they are related. For instance, whether this word is the subject of this word, whether this word is the object of another word. And that's exactly the obj. It means that this $sign is the object of the verb phrasing. And whether the word is a preposition of the verb, in this case, preposition here, whether this word is indicating the number 30 and million will be these relationship between $sign and each child. And also, of course, another object, but this is on the preposition object. So it goes from to depth. Okay, so it's a bit different from how the constituency parser works, but you get how this can be also transformed relatively easily from the constituent parse. So in the early days, people were trying to really translate from constituent parse, of course, using these algorithms like CKY parsing with the PCFG. So with these, you can create a constituent parse. It's very hard to pronounce. And then given these words, this parse, you can translate that into dependency parse relatively easily. That's how people did. And people usually use this dependency parse to do any machine learning task because it's easy to define features. For instance, if you want to measure syntactic distance between two words, it makes more sense to measure the distance in the dependency parse because you don't have any non-terminal nodes. So in this case, maybe you can see that the has distance of 1, 2, 3, 4. So they're pretty far away. So there are several relations that people have defined. Of course, one thing that you need to really be aware of this is that there is no single right way to define the syntax. So these like argument relations are relatively, I would say, can be different depending on who the linguist is or who the creator is. So of course, there are things that all linguists agree on, for instance, subject, object, these things. But then if you get into more details, then different linguists have different definitions. And it gets even more diverse when you get to dependency parsing than the constituent parsing, because it depends on what you're going to relate to and also how you're going to relate it. So I want to say that there is no single way to really define the relations, but this is one very popular way that people define the dependency between words. And you can pretty much understand what's going on. Subject, object, complement, nominal modifier, numeric modifier, etc. The reason why I wanted to discuss this is because for dependency parsing, the recent methods actually approach dependency parsing with neural networks than transforming from the constituent parser. That's exactly called transition-based dependency parsing. Of course, you don't have to use deep learning to do transition-based dependency parsing, but the point here is that instead of going transforming existing constituent parse into dependency parse, there have been efforts to directly predict what the dependency parse of a sentence is without the intermediate constituent parse with a method called transition-based dependency parsing. And you can think of this as constructing the tree in a flattened way. That's why you have this shift right arc, shift left arc. So you have several actions, and these actions allow you to create the dependency parse from scratch. And I think if you can formulate the problem this way, and then I hope that it's very straightforward to see how you can use neural net to do this, right? Because this is exactly how you can use something similar to recurrent neural networks to really mimic this transition. So that's exactly what people have been doing more recently. These are all pre-deep learning papers, but you will see that in the later slides. You basically have a dependency parser that just creates the parse with this by modeling transition with neural networks. And I just want to tell you that it's getting pretty high accuracy compared to previous models. But I think I don't have much time, so I'll be stopping here regarding the dependency parser. But hopefully you get the point. And also, of course, there have been work to simulate the constituent parser with neural networks as well. Yeah, so you can refer to the slides for these other works. Hopefully they are useful if you're interested in this kind of work. But the really important point I wanted to make is that going back to our lecture. Yeah, so again, syntactic parsing is, of course, an important task, but its importance is a bit different these days compared to like 5 or 6 years ago. Okay, so let's devote the rest 10 minutes on semantic parsing really quickly so that you know what the semantic parsing is. Probably I might have to come back to this next class a bit, or the class after our discussions. I'll think about it, but I'll try to cover a few things today. So what is semantic parsing then? Is it different from syntactic parsing? At the first glance, it looks pretty similar in a sense that you're mapping natural language to some structured format. In semantic parsing, we call it logical form. And really important thing in the semantic parsing is that whether the target logic space can vary, what really matters is that the output parse has to be executable. That's a very important thing. It's exactly the point of semantic parsing. You want to translate a natural language sentence into something executable by a machine. And when something is executable, what it means is that the meaning of the sentence is fully defined in that target space. Because otherwise, you cannot execute something. An executable program has everything fully defined formally. So that's exactly the point of semantic parsing, because you have a machine that understands, for instance, SQL query or some complex logic or programming language, but your input side is natural language by humans. Then in that case, you want to be able to map the natural language to the logical form so that the machine can execute it. So I'll give you a few examples, but let's first compare what then differences between syntax and semantics. And one more, which is pragmatics, that you might be also hearing a lot when you compare between syntax and semantics. So syntax is basically the grammar or structure of the sentence. So whereas the semantics is the meaning of the sentence. And one more is the pragmatics is the context of the sentence. So the syntax can be oftentimes rigorously defined. So although we have still some ambiguous cases, we saw that, right? And depends on the meaning of the sentence. But essentially, the syntax is very rigorous compared to semantics because it's pretty clear that you might have several possible options, but it's not like you have like millions of possible options, or it's still possible to actually define your options, right? But then in semantics, it's much more difficult to really define it. Semantics is it's very difficult to really fully define it because there's countless entities, countless relations, and you have to know what the world. You have to have some world knowledge to be really sure about the semantics, etc. So in that sense, then syntactic parsing maybe can be considered as at least the problem is well defined, but semantic parsing oftentimes even defining a problem is very difficult. So in the literature, oftentimes semantic parsing is almost the synonym to mapping natural language to formal language, such as SQL or Python, etc. In I would say something similar to question answering environments. Although it's not limited to question answering. So to be formally speaking, you can do the semantic parse. You can semantically parse any kind of sentence, not just question. You can just parse what I'm saying right now, because it's also will have some meaning and has semantics. There are several ways. I mean that's semantic parsing is not limited to questions, but you might be wondering why all the semantic parsing task is about questions, and it's exactly because that's the number one, the where the most applications happen, and number two, it's easier to evaluate that way because it's easier to evaluate whether your answer is correct or not than trying to evaluate whether your I would say semantic parse is correct or not, which requires a lot more. If you want to evaluate that, of course, through humans, that will be more difficult and also difficult to obtain the data too. So that's why semantic parsing most of the times is really parsing a query or a question into predefined logical space like SQLDB. So what is then pragmatics? Pragmatics is semantics with context. So think of a dialogue. In dialogue, you do not just you cannot guess what the meaning of the sentence without what has been said before the current sentence, right? So you need to know what the context is. So I think so definitely semantic parsing and pragmatics are more difficult than syntactic parsing in general. But the good thing about semantic parsing is oftentimes semantic parsing is directly applicable to many real-world tasks. It's not just giving you the features that you need to do the task, but you're actually solving the task by doing semantic parsing. So what are the examples? One popular example is knowledge graph QA. So when you ask this question, when was KAIST founded? On Google, then you'll get the answer February 16, 1971. And the reason why this answer was obtained is because what Google did was not mapping the question to the answer directly, but they mapped the question to this logical form, KAIST/founded. And you might think that's really simple. So is it even logical form? But it is logical form because when something is logical form when everything is grounded to that logic space. And here KAIST is firmly grounded to the entity KAIST in the knowledge graph in some database, and founded is a property in that database that also this query is grounded on. So this translation task is definitely a semantic parsing task. Although, of course, this example was relatively easy, but it is very useful, right? Because you can ask a lot of different questions. And if that question's answer exists in the database, then you can just formulate this problem as a from natural language to logical form semantic parsing task. You can directly link this to any application that you want to and create a question answering machine. Okay. Another example is natural language to SQL. So it's a bit more complicated because now your target logical form is not just simple entity slash property, but something like this SQL query here. Select count CFL team from some table where college equal New York. And in fact, SQL is probably the most common way to store data. So it makes sense that we want to formulate many problems into natural language to SQL instead of other logical forms. But it was relatively recent that people really delved into NL to SQL problem. Most notably is WikiSQL in 2017, which created a large number of DB natural language and SQL pairs for training so that you can use neural net driven models, especially seq-to-seq actually. Seq-to-seq. So you just basically try to convert the question to SQL with the sequence to sequence model. And more recently, of course, transformer based. And since then, there have been a few notable data sets, namely Spider, Spark, and CoSQL. You can think of these as Spider is a bit more difficult data set than WikiSQL in that they collected data from not the crowd workers who are the non-experts, but they used Yale's PhD students, 11 students who are expert at SQL to create this 10,000 pairs. And they're very high quality in that sense because it's annotated by the experts, not the non-experts from the crowdsourcing company. And two more data sets that have appeared more recently was a Spark and CoSQL. They deal with more of a multi-turn and conversational semantic parsing. And in some sense, you can think of this as a pragmatics too, right? Because you have multi-turn, so it's more of a pragmatics. But I think for some reason, people are more careful about using the pragmatics because pragmatics, the word is like a ultimate term kind of in linguistics. If you can do something about pragmatics, then you basically have like a human-like machine. And I think people are careful about using this word because it's such a big word, pragmatics. Okay, so and there are more classic data sets such as geoquery and ATIS. Geoquery input will be something like what is the population of Iowa, and this also translates into some logical form that is accompanied with database so that you can know whether your output of your model is correct or not easily. And ATIS is for the this is about your query is about something like list all flights from Chicago to Milwaukee, and you basically have a database of the flights, and then of course you output the list. If you output the correct list, then you get the question right. And so classic data sets are smaller than these more modern data sets on the NL2 SQL. So people usually use these data sets a bit more these days because of the size, and also of course it's I would say the domain is a bit more applicable in general. It's SQL. So I think I'll stop here today. We have a few important things about how semantic parser can be modeled, created, either strong supervision or weak supervision. But we can probably go over that briefly in the next class, or maybe after the paper analysis class. So we'll come back to that, but hopefully you get the point that the easiest way to approach the semantic parsing problem is, again, using seq-to-seq. So it is actually a very versatile way of formulating a problem, seq-to-seq. And of course, seq-to-seq, you use transformer-based architecture these days. So I'll wrap up here. I'll see you people in the on Monday's class, because Wednesday's class is canceled. So I hope you can also spend your time working on your assignment this week. Okay, thanks a lot.